Now, in previous lecture, uh, I discussed about concepts of fluids flow, that is the types of fluids flow, and some types of fluids kinematics covered in previous lectures, but some types of some concepts and types of fluids flow are not covered in that lecture. Therefore I covered in that lecture remaining types of the fluids flow. That is here first one is the one dimensional flow. Here three types of fluids flow, like one dimensional, two dimensional, three dimensional fluids flow. Okay, therefore we can say one dimensional flow is what? It is that type of flow in which the flow parameters such as velocity is a function of time and one space coordinate only. Mathematically it can be represented by u is equal to the function of x comma v, where v is equal to 0 and w is equal to 0, where u, v and w are velocity components in x, y, z coordinates respectively given in that types of flow. Therefore we can say easily, or in other words, therefore in one dimensional flow only x-axis, the function of velocity is occurred only the x function of the x-axis, not existence of the function of y-axis and z-axis. Therefore v is equal to 0 and w is equal to 0 respectively. For example of that types of fluid flows, that is the flow in pipe, where average flow parameters are considered for analysis purpose. Now next one is the two-dimensional flow. Two-dimensional flow, see in that picture, the above figure 5.2 is the one-dimensional flow, only one-dimensional flow. The fluids flow in the direction of x-axis only. You see in picture one larger pipe connected to one shorter pipe, and therefore flow in the one direction flow, not in two-dimensional flow. Therefore next one is the two-dimensional flow, the flow in which the velocity is as a function of time and two rectangular space coordinates is called two-dimensional flow. Mathematically it can be represented by u is equal to the function of xy and v is equal to the function of xy. That is the we represent u is equal to f1xy and v is equal to f2xy. And the third coordinate components of the velocity is going to be 0, that is the w is equal to 0. For example, flow between parallel plates of infinite extent and flow in the mainstream of a wide river is like a two-dimensional flow. Therefore a river fluids flow in x direction and as well as y directions, both two-dimensional flow. In given diagram, this is the example of two-dimensional flow, and which is this type of flow is a mainstream of a wide river flow. Now next one is the three-dimensional flow. In three-dimensional flow, it is that type of flow in which the velocity is a function of time and three mutually perpendicular directions. That is the like that, say something about like that. Okay, x-axis, y-axis and z axis, okay, or x, y and z. Three coordinates perpendicular, mutually perpendicular, connected to each others, and therefore the velocity functions u, v and w is f1 xyz, f2 xyz and f3 xyz respectively. Therefore we can say we understand by the that function of the velocity is the velocity u is the function of also the three-dimensional flow, three coordinates flow, that is x, y, z. V is the function of three coordinates, that is x, y, z, and w is the function of three coordinates x, y, z, that is the three-dimensional flow. The example of the three-dimensional flow is in a converging or diverging pipe or channel. Flow in a prismatic open channel in which the width and the water depth are of the same order of magnitude. Therefore, in the example, this is the example of the three-dimensional flow. Now, rotational and irrotational flow. Some the irrotational and rotational flow covered here in see pictures below pictures. This is the example of three-dimensional flow, converging or diverging, and same magnitude of the velocity of the fluids. Now the next one is the rotational and irrotational flow. Rotational and irrotational flow also covered in previous lectures, but here discussing about the rotational flow. A flow is said to be rotational if the fluid particles while moving in the direction of flow rotates about its mass, center of the mass, its own axis, that is the center of gravity. It's rotate about center of gravities. Flow near the solid boundaries, and it is a rotational flow. That is the motion of liquid in a rotating tank. This is the example of rotational flow. Now second one is the irrotational flow. A flow is said to be irrotational if the fluid particles is which moving in the direction of flow, okay, and do not rotate about its mass axis, that is center of gravity. It's do not rotate about its own axis, center of gravity. Therefore these fluids flow are called irrotational flow. For example, flow above a drain hole of a stationary tank or a wash basin. This is the example of irrotational flow. But we can see then that type of example is like similar to the rotational flow, but it is not a rotational flow, it is a irrotational flow, okay. Now laminar flow also covered in previous lecture, but in laminar flow it is a flow in which the paths taken by the individuals particles do not cross to each other and flow separately layer by layer, okay. It is called the laminar flow due to viscosity, and you see in picture this is the laminar flow, and this is the turbulent flow. Turbulent flow is that the flow in which fluid particles move in zigzag paths are mixing to each others, and this is the called turbulent flow. But one types of flow occur in that conditions when laminar to turbulent flow goes to flow is laminar to turbulent. Therefore the transition points, that is the transition points converting to laminar to turbulent flow, it is called transitional flow, okay. This is the mixture of both laminar, some like laminar, some parts are like a turbulent flow, okay. Laminar and turbulent flow are characterized by on the basis of Reynolds number. Therefore for Reynolds number that is it is represented by capital R suffix E. In Reynolds number is less than 2000, flow in pipe is laminar flow. When the Reynolds number is less than 2000, therefore the flow in pipe is called a laminar flow. For Reynolds number is greater than 4000, therefore flow in pipes is turbulent flow, okay. And For Reynolds number in between 2000 to 4000 values of the Reynolds number, therefore the flow in pipe may be laminar or turbulent both. We can say the flow is laminar as well as flow is turbulent. Now compressible and incompressible flows. Compressible flow, it is that type of flow in which the density of the fluid changes from point to point, or in other words, density is not constant for this types of flow. Mathematically, a density is not is equal to 0. Therefore, mathematically, density is not is equal to constant. It is variable. Therefore, flow of gases through orifice, nozzles, gas, there is a turbine, etc. Incompressible flow, it is that type of flow in which density is constant for the fluid flow. Liquids are generally considered flowing incompressibly. Mathematically, density rho is equal to constant value. That is the subsonic or aerodynamics. Okay. Types of flow of lines, types of flow lines, that is the path lines, stream lines, streak lines, etc. Path lines, the path followed by a fluid particles is in motion is called a path lines. Shown in the figure. That is the type of path lines. Stream lines, a way is defined. That type of way it is defined as an imaginary lines within the flow, so that the tangent of the any point on the indicates the velocity of that point. Therefore, we can state that the velocity tangents of any points is which is different for the with comparison to the other point we see in the pictures. Okay, that is the dx upon u is equal to dy upon v is equal to dz upon w. All are equal. Okay. Some characteristics of streamlines. Streamlines is very important. That is, the streamlines cannot intersect itself. Not two streamlines can be crosses to each others. There cannot be any movement of the fluid mass across the streamlines. Streamline spacing varies inversely as the velocity. Converging of streamlines in any particular direction shows acceleration flow in the direction, which is very important. Therefore, I discuss in repetitionally, again repeated that topic. Whereas a path lines gives the path of one particular particle as at successive instant of time. A streamline indicates the direction of number of particles at the same instant. The series of streamlines represents the flow pattern at an instant. Now in steady and unsteady flow. In steady flow, the pattern of streamlines remains invariant with time. The path lines and streamlines will then be identical, and in unsteady flow, the pattern of streamlines may or may not remain the same at the next instant. Now, therefore, the stream tubes. Stream tubes is a fluid mass bounded by a group of streamlines. The contents of a streamline's use are known as current filaments, and we see in the picture some characteristics, some examples of stream tubes, that is the pipes and nozzles. Some points occur here. Number one, the stream tubes has finite dimensions, as there is no flow perpendicular to streamlines. Therefore, there is no flow across the surface called stream surface of the stream tubes. The stream surface functions as if it were a solid wall. The shape of a stream tubes changes from the one instant to another because of change in the portion of the streamlines. Now, next one is the streak lines. Streak line. The streak line is a curved which gives an instantaneous picture of the location of the fluid particles which have passed through a given point. For example, the path taken by smoke. coming out of a chimney or any smokers. In an experimental work to trace the motion of fluid particles, a colored dye may be injected into the flowing fluid, and the resulting colored filaments lines at a given location, given the streak lines as shown in the below picture. So this is the streak lines. Here this is the streak lines. Okay, of smoke issuing for a nozzle and streak lines at T equal to T1, that is the dye injector, and therefore spread here. In case of a steady flow, there is no geometrical distinction between the streamlines, path lines and streak lines. Okay, there are coincident if they originate at the same point for an unsteady flow and for the path flow, streak line flow, streamlines, all are the different patterns. For example, a person giving out with a smoke from the cigarette. This is the example of streamlines, streak lines. That is the backup of their types of flow. Now some examples based on the types of flow. That is the one flow in a given example. In a fluid, the velocity field is given by V is equal to you see in here, which is the given velocity of the fluid flow. V is equal to 3 okay, which is here in that slide. This is the a small example which is based on flow of the fluids. That is the velocity is equal to 3x plus 2yi plus 2z plus 3x square j plus 2t minus 3z into k, where I, j and k is the unit components. Determine first the velocity components, that is the u, v, w at any point in the flow field. Second one are the speed at point 1, 1, 1. That is this is the coordinate x, y, z. See in pictures. And the speed of time, the speed at time is given here. That is the at a time t is equal to 2 seconds at point 0, 0, 2, where this is the components, this is the coordinates. X component is 0, y component is 0, and z component is given as 2. Therefore, in question also classify the velocity field at steady or unsteady, uniform or non-uniform, and 1, 2 or 3 dimensional flow. This is the question given here. Now we come on the solutions. The given velocity field is here. We write now v is equal to 3x plus 2y I plus 2z plus 3x square j plus 2t minus 3z k. Now velocity component. First question, the velocity component that is calculated as u, v, w at any point in the flow field. Therefore the velocity components are u is equal to, comparing the standard equation, therefore the u is equal to 3x plus 2y and v is equal to 2z plus 3x square and w is equal to 2t minus 3z. The coefficient of I, j and k is the velocity components of the given velocity field. Now I come on first second part of the question, the speed at point 1, 1, 1. Therefore the velocity calculated at the coordinate system given in that slide is 1, 1, 1. That is the x is 1 and y is 1 and z is 1. Therefore substituting putting the value of the given equations, velocity components of the given equations as x equal to 1, y equal to 1 and z is equal to 1, you see in here. Therefore the expression u, v and w is how much? Therefore u is equal to 5 and v is equal to 5 and w is equal to 2t minus 3. Here the components, time components already occur. Therefore squaring the velocity components and adding all, therefore v, capital V square is equal to u square plus v square plus w square, and squaring all the velocity components, that is the 5 square plus 5 square plus 2t minus 3 whole square given here. And solving the above equations we get, that is the 4t minus 12t plus 59. Therefore we can say the velocity, speed of the velocity at the coordinates of x equal to 1, y equal to 1 and z is equal to 1 is 4t square minus 12t plus 59, which is the answer. Now third question, third parts of the question is speed at t is equal to 2s at point 0, 0, 2, where x equal to 0 and y is equal to 0 and z is equal to 2. Therefore putting these values in the given equation, velocity components of the equations, that is the u, v and w, we get u is equal to 0, v is equal to 4 and w is equal to 2 into 2 minus here, which is c in here, 2 into 2 minus 3 into 2, that is the minus 2. And now using the standard equation here, v square is equal to u square plus v square plus w square is equal to, putting the value of u, v and w in that equation, that is the v square is equal to how much, that is the 20, and calculating the square root of the 20 is 4.472 units. Therefore we can say the speed at time t is equal to 2s at point 0, 0, 2 is 4.472 units of the value. Now here in the questions asking in that questions velocity field type. Since v at number 1, first point is, since v at given xyz depends on t, it is unsteady flow. Therefore the velocity field is dependent on the time variant. Therefore we can say, or we say that the velocity is unsteady types of flow velocity. Now second one, which is seen here, since at given t velocity, since at given time t velocity changes in the direction x direction, it is non-uniform flow. This is the type of non-uniform flow. And the third one is the third one, which is seen here, since v depends on the three coordinate systems, that is the x, y and z, it is three-dimensional flow. Therefore we conclude the answer is the speed, the velocity is unsteady flow. Since t is changes at the direction of x, therefore it is non-uniform flow. That is the second part. And third is v depends on x, y, z, it is the three-dimensional flow. Therefore the flow is three-dimensional flow. Okay. Now next example given here, we see in example that is the here we see in example, that is the velocity for a two-dimensional flow field is given by, that is the v is equal to, we see in picture, v is equal to 3 plus 2xy plus 4t square I plus xy square plus 3t z. Okay, k component is given as 0. Therefore two-dimensional flow in given questions, asking in the question is two-dimensional flow. Therefore we come on solution. Before the coming on the solutions, find the velocity and the acceleration at point 1 and 2 after 2 seconds. Therefore, the given the coordinate two-dimensional coordinate system, that is x is 1 and y is 2, after time is 2 seconds. Therefore, we come on the solution here. Here the velocity field is given, v is equal to 3 plus 2xy plus 4t square I plus xy square plus 3 t z, where z component is 0 because j component is 0, k component is 0 because the fluid flow is two-dimensional flow, and putting the value of x and y and time t in the velocity components, field velocity. Therefore, v is equal to capital V is equal to how much we calculate in that equation, putting these values in that equation, and here we see the value of the velocity is 25.08. okay, it is clear. Now next one is the acceleration at the point. Now calculate the acceleration at that point, that is the a is equal to, we know that the expression here we see in here the equation a is equal to v dv upon dt, that is the acceleration component, which we can write that equation is u del v upon del x plus v del v upon del y. This is the differential equation plus del v upon del t. Therefore, also given v equal to 3 plus 3 2xy plus 4t square into I plus xy square plus 3 t into j. Therefore, we differentiate the velocity, field velocity with respect to time t. We get here del v upon del x and del v upon del y and del v upon del t. Three types of the values we calculate. Therefore, del v upon del x, therefore the given velocity field velocity is differentiated with respect to the x, which we get 2y plus y square j, and del v upon del t is equal to 2xi plus 2xyj, which is seen here and here, and del v upon del t also calculated. Therefore, del v upon del t is equal to 8ti plus 3j. We see in the slide. Therefore, putting the all values in the given acceleration equations, differential equations, that is the a is equal to putting all these values del v upon del x, del u upon del y and del v upon del t in that equations, and we get u is equal to 3 plus 2xy plus 4t square and v is equal to xy square plus 3t. Putting these values in that equations, we get the answer, putting here the all values in that equations. Therefore, solving the all values, and we have the final equations. Final equation is here, 128i plus 135j. Therefore, the acceleration value of the acceleration is equal to, putting the I and j value 1, 0 and 2. Therefore, the unit component, that the I and j, squaring the I and j components, which is equal to the 1, and therefore the value of acceleration at the point 1 and 2, which is equal to 186.03 units, which is the answer of that equation, that question. Now next example given here, that is the find the velocity and acceleration at a point 1, 2, 3 after 1 second for a given 3-dimensional flow, given by u is equal to yz plus t, v is equal to xz minus t, and w is equal to xy in meter per second. Now we come on the solution is here. Given the value, that is the 3-dimensional flow. The flow field is a type of 3-dimensional flow. It is clear in the given equation, in given question. Therefore, the components of all three velocity components in direction of x, y and z is u, v and w in the three-dimensional coordinate system, that is x, y and z respectively, is u is equal to yz plus t and v is equal to xz minus t. We see here in that pictures that the w is equal to xy meter in meter per second. In that is the unit of the velocity components. Therefore, the velocity at a point you ask by asking by the questions in questions, that is the point given in here 1 2 3, after time is 1 second, that is the 1 second time. Okay, therefore putting these values in the given equations, therefore u is equal to how much? 2 into 3 plus 1, that is a 7 meter per second. V is equal to how much? That is a 2 meter per second. Putting the all values in the given velocity components, and w is equal to here 2 meter per second. Okay, calculate the all velocity components, that is the u components is 7, v velocity components is 2 meter per second and w velocity components is 2 meter per second also. Therefore we know that the standard velocity, that is the point 1 2 3 is how much? That is the 7i plus 2j plus 2k, which is we can write the with the help of the value of velocity components u, v and w. Therefore v is equal to, at the point 1 2 3 is equal to 7i plus 2j plus 2k. Therefore squaring the all the multiplications, all the multiplied parts of the ij and k, that is the components of ij k is 7 2 and 2. Therefore squaring we calculate the we take the square root of that type of these values, these velocity values, and therefore solving these, and we get that is the 7.55 meter per second, which is the velocity components, standards velocity components. That is the find the velocity of the given equation is 7.55 meter per second. Now next one in the questions is asking by you is acceleration. Therefore acceleration at that point 1 2 and 3, which is given. Therefore this is the velocity component we see in the equation, that is the v is equal to yz plus ti plus xz minus tj plus xy into k meter per second, which is given in the equation in the question. Therefore we know that acceleration a is equal to dv upon dt, that is the first derivatives of the velocity are given and are taking the derivatives of the velocity with respect to the time t, and we rearrange or we write the del v dv upon dt in the differential equations, that is the partial derivatives of that equations is here, that is the u del v upon del x plus v del v upon del y plus w del v upon del z, where capital V is the standard complete velocity components of the whole velocity field components, velocity field plus del v upon del t. Therefore the all values are calculated above, that is the del v upon del x, del v upon del y, del v upon del z and del v upon del t, calculating with the help of the given velocity field field. Therefore rearrange or calculate these equations coming on this equation, after coming these equations, and final results is given here. We see this equation, 10i, that is the acceleration at point 1 2 3, 10i plus 23j plus 26 plus 16k plus 1i minus 1j, that is the acceleration at point 1 2 3. Therefore now we conclude that with the help of the above situation, the convective acceleration components are 10, 23 and 16 meter per second. That is the convective acceleration, a type of convective acceleration. Also discussed in the previous lectures. That is the convective and temporal accelerations or local acceleration. Now the local acceleration components are, that is the 1 and minus. Here we conclude with the help of this, that is the 1 and minus 1 meter per second along the x and y directions. Okay, therefore the total acceleration of the fluid particles at the point 1, 2 and 3, which is asking in the questions by you. Therefore the acceleration at point 1, 2, 3 is equal to, putting these all values, 10 plus 1 whole square plus 23 plus minus 1 whole square plus 16 whole square, which is the value of accelerations components, convective and temporal or local accelerations. Therefore solving these and taking squaring root of that value, which is we get 29.34 meter per second square. Hence we can say the acceleration at point 1, 2, 3 is equal to 29.3 meter per second square. And the questions and the asking by in that questions, which is concluded and which is. Now again solving next example, that is the given example. Here we see in that example, that is the velocity v given in the equations, that is the v is equal to 2t multiplied by 1 minus ax upon 2l. Okay, the velocity along the convective of a nozzle of length L is given by, where L is the length of the nozzle. Okay, we don't confuse. Where capital V is the velocity which is given in your questions, that is the velocity, that is the V is equal to capital V in meter per second, which is given in questions. That is the time in a second, that is the t from commencements of flow. X is equal to distance from inlet to nozzle, that is the distance. And now calculate in that equations which is asking here, calculate the convective acceleration, local acceleration as well as total acceleration when the time t is equal to 6 seconds and length of the nozzle is equal to x is equal to 1 meter and L is equal to 1.6 meter, which is given in that equations, that questions. Now we can solve these equations. We are solving these equations. Here solution of the equations is here, that is the velocity along the center line of a nozzle v is equal to, given here 2t 1 minus x upon 2l whole square. Therefore local accelerations, now taking the velocity, now taking the partial derivatives of that types of the given velocity field with respect to t. Therefore del v upon del t is equal to 2 1 minus x upon 2l whole square at given time t is equal to 6 seconds and x equal to 1 meter. Putting all values in these equations, we get the value of the local acceleration is 0.945 meter per second square. And now we calculate the convective acceleration, that is the v del v upon del x. This is the partial derivatives of the velocity components with respect to the x, that is the v multiplied by del v upon del x is equal to multiply by, this is the v velocity field and here is which is the partial derivatives with respect to the x of the velocity field. And now solving the above, we get minus 4 t square upon L into multiply by 1 minus x upon 2l whole square whole cube, and therefore we come on the solution of that equations, above equations. And now putting the value time t is equal to 6 second, and length of the nozzle x is equal to 1 meter. Therefore convective acceleration is here we calculated, and the convective acceleration in terms of negative terms, that is 29.24 meter per second square. Therefore total acceleration is equal to local acceleration plus convective acceleration. Add on both accelerations, therefore adding both accelerations, therefore we get the answer is minus times negative sines 28.295 meter per second, which is the answer of the total acceleration. Okay class.